Hi, welcome back to Math 533, Topics in Euclidean Geometry. And welcome to week 14 of the semester. This is our final week. In this video, we're going to be looking at two things. The first thing we're going to look at is how area transforms under similarity transformations. And then we're going to use that to build us a third proof of the Pythagorean theorem. So this third proof will combine the idea of similar triangles and the idea of area. Okay, let's take a look at how area behaves under similarity transformations. Let T be a similarity transformation with some ratio C that is positive. So in my picture here, I have my original rectangle in black, and the image of it here is in red. And I believe I chose my ratio to be something like 3/4. But this doesn't matter, right? You can take any ratio at all. And this will send, right, if I have a rectangle whose sides are x and y, it's going to send it to some rectangle that has sides cx and cy. Right? That's by definition of a similarity transformation. And the area of my original rectangle is x times y, and then the image is of area, I should say, cx times cy, which is c squared times xy. So on rectangles, it scales the area by a factor of c squared, and then since our area was defined in terms of rectangles and decompositions, that means that T scales area of any shape by a factor of c squared. Now I should point out, this is something that you know already from your real life, right? If I have a, let's see, 1 square yard, if you imagine that, that's 9 square feet, right? It's not 3 square feet, it's 9 square feet. And volumes are going to scale like a cube of the scale factor. So now let's look at a pictorial representation of what happens with a triangle when I scale it by a factor of 3. So here I'm thinking of ABC as being my original triangle, and I apply some similarity transformation. So here I'm thinking of a dilation centered at A of ratio 3. So here I now have my bigger triangle A, B prime, C prime that I got by dilating the triangle ABC with a factor of 3. And now in this picture we totally understand, right? We're saying that the area scales by a factor of 3 squared, so in other words 9, but we can see it geometrically just by decomposing our big triangle into 9 little triangles, each of which is congruent to our original ABC. Right? So here I have ABC, and then I have 1, 2, 3, 4, 5, 6, 7, 8, 9 little triangles decomposing the big triangle. Right? So this at least is consistent with what I was claiming from the previous slide. Okay, now that we've seen how area behaves under similarity transformations, we're ready to take a look at my favorite proof of the Pythagorean theorem. Now this proof is going to be very conceptual. It's not going to have as pretty a picture as the second proof that we saw last week. However, I think it gives a really good feeling for how the Pythagorean theorem, similarity, and area all kind of talk to each other. Now this proof is, I've seen many attributions for it. Frank Wilczek, the Nobel Prize winner, attributes it to Einstein. Einstein, in one of his autobiographical writings, mentioned that he proved the Pythagorean theorem as a child and had a beautiful proof involving similar triangles. Nobody knows exactly for sure which proof he had in mind. I've also seen this proof attributed to John Conway. And then I've also, I learned it personally from lecture notes by Alexander Givental. I'll also give a link to that in the description box. And Givental makes reference to Polya, a mathematician who wrote a very famous book in the 50s on how to solve problems and how to teach problem solving. So for those of you interested in education, I do recommend taking a look at Polya's books. They are deservedly classics in teaching problem solving. Polya, in turn, attributes this proof to Euclid himself, though not the first proof that Euclid gives in the Elements. It's a proof that Euclid gives in, I believe it's in book 6. Okay, and then as I kept searching, I found more attributions for where this proof of the Pythagorean theorem comes from. So independently of its attribution, let's go ahead and think about what is, in my opinion, one of the most beautiful proofs of the Pythagorean theorem. Let's go. So let's set up this problem exactly the same way we did before. So I have a right triangle ABC, and I've labeled the sides by the vertex opposite them. So for instance, BC is opposite A, so it's a lowercase a. AC is opposite the vertex B, so I label it with a little b. And AB is the hypotenuse, and I label it with a little c. So now I drop the altitude from C, and I label the foot F. And by the argument we saw last time, gives us that triangle ACF is similar to triangle ABC, and triangle CBF is also similar to the big triangle. Right? So each of these two small triangles we have here are in turn similar to the big triangle. And I want to point out, right, so the triangle CBF has little a as the length of its hypotenuse, and triangle ACF has little b as the length of its hypotenuse. Right, so we have three triangles that are right triangles, and they have lengths of hypotenuse given by C, by A, and by B. So now let's look at the areas of these three triangles, and we're going to look at them in two different ways. So the first way is by decomposition. We're going to see our big triangle as being made up of the two smaller triangles. So here I have colored ACF in green, and BCF I have colored in blue, and ABC I have surrounded in red. Right, so the big triangle is obtained as the union of the two smaller triangles, and by our decomposition axiom for area, the area of the big one is the sum of the areas of the two little ones. Now the second way we're going to look at this is by looking at similarity. So this is the perhaps slightly subtle part. So the big triangle ABC is similar to the triangle ACF, right, the slightly smaller triangle, and the ratio between them is going to be the ratio of the hypotenuses. Right, so the hypotenuse of ACF has length b, and the hypotenuse of ABC has length c. So the ratio, the scaling ratio we have between them is the ratio of the two hypotenuses, b over c. Okay, same deal in the other small triangle that we have. Right, triangle ABC is similar to triangle CBF, and the ratio I take, right, I take my favorite corresponding pair of sides, and in this case I'm taking the ratio of the two hypotenuses again. Right, so we have CB, which is this little a over here, right, that's the hypotenuse of CBF, and I take the ratio over the side AB, which is the hypotenuse of my big triangle. So I get A over C. So now by the area scaling law that we saw at the very beginning of this video, the area of ACF is that ratio B over C squared times the area of the big triangle ABC. Right? So I've simplified B over C quantity squared as B squared over C squared. And similarly here I get A squared over C squared. And now we combine these facts. I'm going to say that the area of the triangle ABC is equal to the sum of the two smaller areas. And then I use the identity that we just proved. Right? So this is the area of our first little triangle, and that's the area of our second little triangle. And now I have a common factor of the area of the triangle ABC. The area of that triangle is non-zero, so we divide both sides by it, and that gives me that 1 is then equal to the, okay, so I've written it in the other order, right? So A squared plus B squared over C squared. And now we just multiply both sides by C squared, and that proves the Pythagorean theorem for us. Okay, that's it for this video, and that's it for Math 533. I hope you enjoyed this proof of the Pythagorean theorem. It's one that makes me very happy. It gives me a lot of joy to think about this proof. Do think about it. But this is the end of 533. We will have one more little recap video, but this is the end of the content. I hope you've enjoyed everything, and there are many places you can go for further, if you have further interest in geometry. We've only scratched the surface of Euclidean geometry, and then of course there's all the geometry that's not Euclidean that's out there. Thank you for watching. Happy mathing.